Welcome back everyone to Learning by Teaching. Today we're in dynamics and we're going to solve problem 12.43. Okay, it says the motion of a jet plane just after landing on a runway is described by the AT graph. Determine the time t prime when the jet plane stops. Construct the VT and ST graphs for the motion. Here S is equal to 0 and V is equal to 300 feet when t is equal to 0. Okay, so what we have in here is that we have this jet plane and it just arrived, it's just landing, and the acceleration is described by this graph. Okay, so what they're asking us is to find the t prime when this jet plane stops. In other words, when the velocity is equal to 0. The problem is that we need to find the velocity and then we need to find it because we have the acceleration. So in order to find this velocity, and then we also need to find this position in order to construct the SC graph, what we need to know is that our acceleration is equal to the change in velocity with respect to the change in time. And if we want to find velocity, what we can do is solve for the change in velocity, which should be equal to our acceleration times the change in time. Now if we perform an integral in both sides, we will then find velocity, and then also after finding velocity, we also know that there is a relationship between velocity and the change in position with respect to time. And if we solve for our change in position, this should be equal to our velocity times our change in time. And then same thing that we did for our velocity. In order to find our velocity, we do an integral on both sides and we found our position. Okay, so let's start solving this problem. So what we can see is from 0 to 10 we have a different acceleration. Then we have from 10 to 20 we have this different acceleration, and from 20 to our final time we have this acceleration. So we're going to break these time intervals by 10. So let's start between 0 and our time all the way to 10. What we can see from the graph is that our acceleration is just equal to 0. So we got 0 acceleration. So acceleration is equal to 0. If we want to find our velocity, now we know that we will do the integral of our change in velocity. Well, what is our initial condition for velocity? Our initial condition is that velocity was 300 feet when time is equal to 0. So we got 300 feet per second. Our final velocity, we're just gonna assume, is equal to v. And then we have our acceleration times our change in time. What happening here is that our acceleration is equal to 0. Therefore, everything in here multiplied by 0 gets equal to 0. So we'll have that all that is equal to 0. Okay? If we solve our integral on our left, we'll find out that we'll have v minus 300 gotta be equal to 0, and if we solve for our velocity, this should be equal to 300 feet per second. Okay, so this is our first equation, and we're going to mark this as our first time interval. Okay, our time intervals, we're gonna mark it with green, and our equations that are important with blue. Okay, after finding our velocity, what we can find is our displacement. And as we said before, the integral of our change in position has to be equal to the integral of our velocity, which is 300, multiplied by our change in time. For our boundary conditions for these two integrals, where on the left we're talking about position, so we need to know the initial condition of our position. We're going to go back to the problem statement, and we'll see that s is equal to 0 when time is equal to 0. Okay, so s is going to be equal from 0 all the way to our final position. In our time, well, we already specified that we're talking from 0 all the way to 10. But instead of putting 10 in here, what we're going to do is that we're going to place t for just to leave our equation in terms of time. Okay, so if we solve these two integrals on our left side, we're gonna have that our position has to be equal to 300t. Okay, and this is our second important equation. Okay, Now for this first time interval, we solve for velocity and position. Okay. Now we're gonna go and jump to a second interval that is gonna go from 10 all the way to 20. And what I'm going to do is that I'm going to paste our picture in here just to keep working on it. And in this case, it's gonna be important. So I'm going to highlight this in green because this is our second important time interval. And as we can see in here, our acceleration from 10 to 20, it's a linear equation that we don't know. Okay, so we need to find that out. What we know about a linear equation is that a linear equations are y in the form of y equals mx plus b, right? So for our slope, which is our m, we know that it has to be the rise over the run. But our rise is 10 and our run is 10, meaning that our slope is a ratio 1/1. So we know that our m is equal to 1. In this case, if we say our x coordinate is our time interval, so we're gonna put 1t. Now, what will be the y-intercept if this line is a 1/1 ratio? Well, if at the time that I'm here, so let's erase this, at this time where I have this red dot in here, right, it's 10, -20, and I'm going backwards 10 amount in a ratio of 1/1, this should hit me -30. So our y-intercept should be -30. And then we have that our y, in this case our acceleration, has to be equal to 1t minus 30. Okay, I know this is a really kind of like a different way of solving for our acceleration equation, but if you guys are not comfortable with this way, you can go back and put any method that you learn in algebra. Okay, so now that we know that our acceleration is equal to t minus 30, we're gonna go ahead and do the integral of our change in velocity. Now, what is the initial conditions of this velocity? Well, the initial conditions has to be at time when equals to 10 seconds. Do we have an equation when time is equal to 10 seconds? Yeah, in here, this equation is valid from 0 all the way to 10. So we know that our initial condition of our velocity, so our velocity when time is equal to 10 has to be equal to 300 feet per second. It doesn't vary from 0 to 10. And we will also need our initial condition from our displacement. And if we put into this equation that time is equal to 10, we will have 3,000 feet, okay? So I'm going to erase this just to not get confused. And for our integral on our velocity, we're gonna have 300 all the way to our final velocity has to be equal to the integral of our acceleration. Well, our acceleration is t minus 30 multiplied by our change in time. And then we have that the time goes from 10 all the way to our final time. We know the final time for this acceleration is 20, but we're going to just keep it in variable form, okay, as t. We're going to solve the integral on the left, and we will realize that this is equal to v from 300 all the way to our final velocity has to be equal to t squared divided by 2 minus 30t, and this is going to be evaluated from 10 all the way to our final time. If we solve our initial conditions on our left, we have v minus 300 has to be equal to t squared divided by 2. On our right side, we're going to replace t by t, so just everything keeps the same, minus 30t minus, and then now we're going to replace our t's for this 10 in here, okay? So I'm going to open a big bracket, and we're going to have 10 squared divided by 2 minus 30 multiplied by 10, okay? Now we're going to have that our velocity has to be equal to, I cannot combine this t with anything else, so they will stay the way they are, t squared minus divided by 2 minus 30t minus, and then we're going to plug in all that we have in here into our calculator. So let's see how much that is. So we got 10 squared divided by 2 minus 3 times 10, and this will give me a total of negative 250. And we also have negative 300 that we're going to pass to the other side, which will be positive 300. Okay, just to double check, we have a minus and a minus. These two guys will become a plus. Okay, so we got that our velocity is equal to t squared divided by 2 minus 30t plus, and then we have plus 250 plus 300 will give me a total of 150. Okay, and here is our third important equation for velocity. Now that we know our velocity, we're gonna go ahead and find our position. So we know that the integral of our change in position. Okay, now what is the initial condition of position? Well, we found that one over here, which is 3,000 feet. So we're gonna put from 3,000 all the way to our final position. Has to be equal to the integral of our velocity. Well, velocity is t squared divided by 2 minus 30t plus 550. Okay, multiplied by the change in time. We are just missing the boundary, the initial conditions for our time. And the time, as we stated before, is going to go from 10 all the way to our final time. If we solve the integral on our left, we're going to get s, and it's going to be evaluated from 3,000 to our final position s, has to be equal to, and then if we perform the integral on our right side, we'll have t cubed divided by 6 minus 15t squared plus 550t. And these are going to be evaluated from 10 all the way to t. Okay? If we solve our boundaries on our left, we will have s minus 3,000 has to be equal to, now we're going to replace our t's for this t, so nothing changes it really. We're gonna have t cubed divided by 6 minus 15t squared plus 550t minus, and then I'm gonna open a big parenthesis because we're gonna replace our t's for this 10. Okay, so we're gonna have 10 cubed divided by 6 minus 15 multiplied by 10 squared plus 550 multiplied by 10, and we close our parentheses. Okay, if we solve for our position, so s is going to be equal to what? All these variables that had t, we cannot combine them with anything else, so we're just gonna leave them the way they are. T cubed divided by 6 minus 15t squared plus 550t minus, and then the bracket. So we're going to put everything that is in the bracket in our calculator, and when we do that, we will realize that this is equal to 4,167. Okay, and we're gonna do at the end plus 3,000 because it was on the other side negative, so passes to the other, to this right side as positive. If we simplify for our position, we will have an equation of t cubed divided by 6 minus 15t squared plus 550t, and we're gonna end up with negative 1,167. Okay, so we just found our fourth equation that is important in this problem. And as we did before, we needed to evaluate and find the final velocity at these intervals and final position at the time interval. So our final time interval in this case is 20. So we're going to evaluate these two equations when time is equal to 20. So if we do that, so we're going to do velocity when time is equal to 20. What is this equal to? So we're going to take this equation and we're going to put for t equal to 20. Okay, so we're gonna have 20 squared divided by 2 minus 30 times 20 plus 550, and if we plug that into our calculator, we will see that that's equal to 150 feet per second. Okay, And also we're going to do the same for our position. Just put when time is equal to 20, and we're just going to have 20 cubed divided by 6 minus 15 multiplied by 20 squared plus 550 multiplied by 20 minus 1167. Okay, so if we plug this into our calculator, when time is equal to 20 will be equal to 5167 feet. Okay, so now that we have this equation, I'm sorry, 5166 feet. So now that we have the initial conditions for the next time interval, so we're going to start with our next time interval that starts from time equal to 20 all the way until a time that we don't know, that it's actually what we're trying to look for. Okay, so we're just going to highlight our time interval just to make sure we are doing a new time, and we're going to put our graph in here again so we know what is our acceleration. Okay, so we have that our acceleration for this time interval is equal to -10. Now, since our acceleration is equal to -10, we're going to have that the integral of our change in velocity has to be equal to the integral of -10 multiplied by the dt. We're just missing our boundary or initial conditions, which for our velocity is 150 all the way to our final velocity, and our time starts at 20 seconds and it ends at a time interval that we don't know yet. We're just gonna call it t. Okay, if we solve the integral on our left, we have v evaluating from 150 all the way to v, and this is going to be equal to -10 t, and it's going to be evaluated from 20 all the way to t. Okay, if we solve on our left, we can have v minus 150 has to be equal to -10 t minus, and gonna open a parenthesis of -10 multiplied by 20. Okay, so now that we know this, we're going to solve for our velocity, and we're going to have -10 t minus, and then in parentheses we got -200, and then we're gonna have plus 150 coming from the other side. Finally, if we solve for our velocity and we simplify it all the way, we're gonna have plus 350. Okay, so we just found another important equation for this problem. Now that we know our velocity for this time interval, here we go again, and we're going to do our position. So we know that the change in position from our initial condition, well, our initial condition was 5166 here when t was equal to 20, so 5166 all the way to our final position has to be equal to the integral of our velocity, which is -10 t plus 350 t multiplied by our change in time, and then the time starts at 20 all the way to a final time that we don't know. Solving the integral on our left, we have s being evaluated from 5166 all the way to our final position has to be equal to -5t squared plus 350 t. Okay, I apologize, I added this t in here, which I shouldn't have. Okay, and we're going to evaluate this integral. So coming back to our problem, we're going to evaluate from 20 all the way to our final t, and we have that our position minus 5166 has to be equal to -5t squared plus 350t, because we're replacing t's for this t, and then we're gonna have minus, and I'm gonna open a big bracket. We're gonna replace our t's for this 20 in here. We're gonna have -5 multiplied by 20 squared plus 350 multiplied by 20. If we solve for our position, we will have, so let's start. This t, these terms that have t on them, we cannot combine them with anything again. So we got negative 5t squared plus 350t minus, and then let's see how much it's everything that I have on the parentheses. I put it in the calculator, and this gives me a total of 5,000 even, okay? And then we have plus 5,166 that is coming from this side of the equation. If we oversimplify for negative 5t squared plus 350t, then we're going to have plus 166, okay? Because we got negative and positive in here, they subtract. And we got our final equation for this problem, okay? So now we're gonna go back and see what was the actual question of this problem. It says determine the time t prime when the jet plane stops, and we need to construct our VT and ST graphs. Okay, so let's start to determine the time t prime when the jet plane stops. And what we're going to utilize is that we're going to utilize our velocity equation. Okay, so I'm going to take this velocity equation in here, and I'm going to say, well, when our jet plane stops, that means that our velocity is equal to 0. So I'm going to put our velocity equal to 0, and we're going to have negative 10t plus 350. If we solve for our time, we will have 350 divided by 10, and we will note that this is equal to 35, and this is in seconds. And we just found the first answer of this problem, okay? So I know it took a really long time to find the time of this problem, but then the second question is to construct the ST and the VT graphs of this problem. Since the video is gonna be super long, what I've done is that I took some pictures of the problem, and then I'm going to display them in here. Here is our ST graph, and then we also have our VT graph in here that I took some screenshots of, so that way the video is not that long, okay? I hope you guys like the video. Please push the like button, subscribe, and I'll see you guys in the next one.